This is one convoluted looking setup, especially when zoomed out a bit. This project adds a FET controlled power switch to the capacitive soil moisture sensor project that I did a while ago, which I'll link below. The original project basically did not have a FET here, and the 5 volts was connected straight up to the Arduino 5 volts. So it would measure the moisture level with this sensor and display results with 4 levels between dry and wet on the OLED display. Now we've added this P-channel MOSFET to turn the sensor on only when it's time to make a measurement, and leave it turned off to save battery power for the rest of the time. This sensor draws about 5 milliamps. I actually measured mine as drawing 5.4 milliamps when on. So using this FET to power it on only for a little bit of time to make a measurement, it's way more efficient. The way the P-channel MOSFET works as a load switch, where V in this case would be our 5 volts coming from the Arduino, and V out would be the 5 volts that powers the capacitive sensor. This TI app note shows a few ways that it can be done, and it's similar to this onsemi app note, but I like the way onsemi draws their FET symbols. I don't really like this TI method, but in all cases we are looking at P-channel MOSFETs. Wikipedia has some info on these various circuit symbols. So for a P-channel, there's all these representations. I am using a P-channel enhancement mode MOSFET. So this is the symbol. A depletion mode MOSFET would have a solid line right here instead of these dashed lines for enhancement. The main reason I wanted to look at the TI datasheet is to show that the simplest circuit to control a load power switch is just the P-channel FET. You throw 5 volts here, you will get a switchable 5 volts out based on this gate having the appropriate voltage. This is the P-channel enhancement mode FET that I have on hand, a TP2104. So I'm going to use this one, even though it's not the most ideal for a load switch. This one has a relatively high RDS on of 6 ohms. Usually it's going to be tens of milliohms or so. So, electrical characteristic chart for the FET, VGS threshold. You'll start turning on the gate when voltage on the gate is 1 volt below our input of 5, and the gate is 2 volts below our source of 5, and we're actually going to be giving it either 5, the same as the source input, or we're going to give it 0. So we're going to give it -5. So that's enough to make sure the FET is turned on. The absolute maximum, we can have a gate source voltage up to plus or minus 20 volts. So we give the gate 5 volts, V gate to source is 0 because we got 5 minus 5 is 0. The FET is off. We need at least -1 to -2. We give it 0 here. Voltage gate to source is now 0 minus 5, or -5 volts, gate relative to source. We give it 0, we turn on the FET because we have at least 2 below 5, with more to spare. The FET is turned on, we get 5 volts out. These other circuits here, well, with this resistor pulling the gate to the input or the source, we don't really need that in our circuit, but I have it there anyway just to keep the FET guaranteed in an off state while the Arduino is booting up, and this GPIO that we're going to put here hasn't been configured properly yet, and so the gate is just going to be flailing around. So we want to try and keep the FET turned off by bringing the voltage the same as the input through a pull-up. Then we can drive it low, or drive it high, or leave it high impedance and it will be pulled high to turn it off. It's just good practice. And as for this transistor here, we don't really need this. One advantage to using it would be to invert the logic. Here we have to give a logic low to turn it on. Over here with this N-channel FET, we would give it a logic high to turn it on, bringing the gate to low. But otherwise, another reason to do this, if you're driving this from a GPIO, that could have its logic low, not a solid ground. You might be able to get up to 0.8 volts on a GPIO output, and it's still a valid logic low when you're reading it in on another device. but that's not necessarily going to turn the FET on as strongly. In our case, I think our FET will still be turned on strongly enough. Doing something like this, when you turn this FET on, you're giving the strongest possible logic low here to turn this FET here on as strongly as you can. Maybe if you're trying to draw a lot of current through here, you'd want to try and make sure you're turning this FET on as good as you can. But we're okay with this. I just added the pull-up resistor, but I don't even probably need that. These component extras are more about controlling the turn on and turn off time of the FET, because if you have a high load current here and you have a lot of capacitance, so you turn this FET on and you've got a high inrush current, doing things like this will turn the FET on more gradually and turn it off more gradually, so you don't get this huge inrush current surge through here. In my circuit, powering this sensor, it's not really a big deal, especially just on the workbench, so I can get away with a simple circuit. So the new FET power switch circuit right here, the pinouts are source, gate, drain. I wrote that here for a reference. So on the source, we have 5 volts. On the gate, we have our pull-up 10K resistor to the 5-volt source, and we are going to Arduino's digital pin 2 to turn it on and off. The drain, which is our 5-volt output, is going straight to the 5 volts input of the capacitive sensor. So this will see 0 volts when the FET is off and 5 volts when the FET is on. Now the Arduino can turn this gate on, give the sensor a little bit of time to power up, do a sensor reading on analog 0, and then when it's done, turn off the FET to disconnect 5 volts and wait till it's time to read again. Having this sensor powered off for hours or days at a time and only drawing the 5.4 milliamps when you need to take an actual reading should greatly improve battery life if this is going to be out in the garden or on the lawn in a wireless setup. We don't need to go through the entire sketch again, it's already been covered in the first video, so let's just look at the differences to get this FET power switch. I'm assigning digital pin 2 as my power output FET switch pin, and to turn the FET on, the gate needs to be low, so I've defined power on as low, power off as high. In the setup routine, I set the pin mode of the FET gate control as an output, and I set it to turn the FET off. Then in the main loop, when it's time to read, I will say on the OLED display that we're reading, then I will set the power on condition on the FET gate, and this is a long time. I'm waiting 2 seconds just to give it time to power up. Then I do the analog reading, and then I turn the FET gate off and do the usual thing to figure out what the reading meant, display the status, whether it's dry, moist, damp, or wet on the OLED, and after I've displayed the status, I wait 3 seconds, and then I write on the display that we are idle because we're not doing anything, the sensor is powered off, and that would represent hours or days between readings, but I'm simulating that with just another 3-second delay. Then when we go through the loop again, I show that we are actually reading, so I know that I am turning on the FET and I'm doing a reading. So let's go see how this looks. So I'll just go through it overall and in stages to try and focus in on certain areas. For now, I have an analog Radio Shack old 80s voltmeter showing 0 and 5 volts going on and off. Then I have my fluke meter as an ammeter in series with this capacitive soil moisture sensor to show me the current in milliamps. It's drawing 5.4 milliamps at 5 volts. Here's the capacitive soil sensor itself with the epoxy to help make the board edges water tolerant. Here's my water, colored green for visibility, so I can use that to simulate the most wet soil condition, and in the air it's got the most dry soil condition right now. The Arduino Uno is hiding right here, and here's the OLED display showing the status, and right here is the P-channel FET turning the 5 volts to the sensor board on and off. Here's a better view of the circuit. The P-FET has pinouts from left to right, source, gate, drain. So the source is connected straight to the 5-volt bus. The gate has a pull-up resistor to the source, 5 volts, and the gate also goes to this digital pin 2 on the Arduino. And the drain pin, which is the 5-volt switched output, comes over here and goes to the capacitive soil moisture sensor. The display shows, when idle, that everything is powered off, and that would simulate if we are actually going to use this to monitor soil day to day. The idle period could be many hours or even days, depending what way you want to monitor. So idle is just a couple of seconds here, then it says reading when it has turned on the power. When it's taken a reading, it turns off the 5 volts and says whether it's dry, wet, or anything in between, and it'll time out and go back to showing that we are idle. So it's been saying dry because we are just in the air, but if I put this straight into the water, it should go to the most wet reading. Now it changed to wet. So if I take it out of the water, it's still going to be a little wet, so let's see if it shows something in between. Moist. And eventually all the water is going to evaporate and it will change toward damp and then dry. See if I can help dry it off a bit. Oh, it went straight to dry. And here's a wider view of the messy setup, and all of this, it's not as bad as it looks. It's really just a bunch of meter probes and alligator clips and Arduino DuPont hookups in order to get everything in one spot, and everything is taped onto the desk. The Arduino and the breadboard are sitting on top of this analog meter, so there's only so much I can do. And this keypad made a cameo appearance. So that's the FET power switch circuit in a nutshell. Here's a close-up of the analog meter. It's on the 15-volt maximum voltage scale, so the 15, 10, 5, and 0 are the numbers we're reading. So it goes from 0 straight up to 5, and when the FET is turned off, when the voltage drops almost to 0, it kind of stays a little higher and glides down a bit. That's just the residual capacitance in the probe itself. So if I unplug the probe so it's no longer being driven by the FET switch, now it should drop really fast to 0. And when I plug the probe back in, it kind of hovers again and gradually goes to 0. FETs as power switches. Very useful.